So let me welcome everyone. Good morning, good evening, late evening, whichever part of the world you are in. So we start with session 3, Energy and Environment, which is UN SDG 7 and 13 goals. And we have the first speaker, who is from Waterloo Institute for Nanotechnology, Professor Linda Nazar, who is a professor in the Department of Chemistry at the University of Waterloo. Linda, please.
So good day, evening, etc. to everyone, and great to be at this workshop. Thank you for the invitation to speak. I was asked, I changed the title of my talk a little, just to make it more on the role of nanotechnology in electrochemical energy storage. And my task today is really to explain to you where nanotechnology comes into electrochemical storage. And I couldn't have had a better setup, I guess, from Dr. Sipp's previous talk, where she pointed out the importance of batteries and also nanomaterials. So indeed, innovation in energy storage is required, and to a large extent it will occur both through the implementation of nanomaterials, but also through control of the interfaces at the nanoscale. So, we're looking to go from Volta's battery to truly advanced rechargeable batteries, sort of schematically described here. People often fail to realize just how much science goes into a battery. So this is a positive and negative electrode. The electrolyte is this gray material in between in which the ions are carried, and electrons are forced through the external circuit, either in either direction, depending whether this is going into charge or discharge. And so we have mass transport issues within both electrodes, moving these ions and electrons around. And we also have issues with reactivity at the interfaces, which are either very high positive potential or very low negative potential. And that causes the electrolyte, to a certain extent at least, to degrade and form these interfacial layers, which can really impede the battery. So at one hand, we want these materials to be nano in order to enable mass transport of the electrons, but on the other hand, we don't want these materials to be nanoscale because we accelerate the degradative reactions of the electrode. And so it's kind of a balancing act to try to obtain materials that work really efficiently and reliably and cycle in a stable sort of way. So I don't think I need to remind you just how important rechargeable batteries are as a platform for sustainable energy, both for the grid, for cars, for planes, where by 2040, Norway's short-haul commercial flights are anticipated to be all electric, and also in robots. Nobody wants a plug-in robot, and with robots and the new demands for artificial intelligence, these represent tremendous markets. So if we think about going from innovation in this energy storage space, we can consider going from incremental significant to disruptive. So personal electronics are a fairly mature area. These are emerging markets, both for electric vehicles and the grid, and electric flight is a disruptive technology, which one might consider to be more visionary. And the batteries that drive these materials are also very different. So, of course, for personal electronics, we have our pretty traditional lithium-ion batteries. And now people are starting to incorporate silicon into the negative electrode as opposed to carbon, and they're trying to make advances in the positive electrode material. But more emerging technologies are in aqueous batteries, in advanced lithium-ion, especially in solid-state lithium cells. And of course, disruptive technology, especially for flight, would be, for example, lithium-sulfur. And so the risks to this range from modest to significant to high. And I'll be talking mostly about, today, just a few examples in aqueous and solid-state technology. But I remind you that to drive all of this, we need to go beyond the research and development into new policies, regulations, and business models. And that is particularly important. It has been, I think, addressed in today to some degree. So as I mentioned, nanomaterials are actually necessary for advanced batteries, not the sort of traditional ones that we have today. And even in the traditional ones that we have today, at the positive electrode, we have these, as I said, materials which they're sitting at a very high potential, and they require surface nanolayers to inhibit the electrolyte oxidation. So these are actually produced more or less in situ by the careful reaction of these electrolytes that are designed to produce such layers. And they don't really work very well, but they work sort of as best as possible. And the negative electrode, as I mentioned, silicon is now replacing carbon in the form of these nanocomposites where the carbon and the silicon have to be intimately mixed. And this is necessary because silicon expands and contracts tremendously on lithium uptake. And so the nanotechnology is needed to control and mitigate that expansion. But what's even more interesting going forward in next generation technologies are batteries based on zinc, so divalent ions that have sluggish transport within the solid because of their high charge. Next generation systems, which as I mentioned include lithium, sulfur, and zinc air, solid state batteries, and also the holy grail, which is to switch the negative electrode from something like carbon, which is what it is now, to lithium metal. And this requires designing nano layers as interfaces. So I don't have time to talk about all of this. I'll just talk briefly about two technologies that we have been actively engaged in. So with respect to the grid, I think it's fairly obvious that intermittent renewables need energy storage. This is to feed back into the grid, for example, to charge EVs. And in this sense, dispatchable power is absolutely vital. And so the levelized cost of electricity is falling faster than either the renewable or the storage, which is really interesting. And the storage is really moving beyond these first adopters. And so there's lots of examples of this market really opening up around the world. Here's an example in South Australia with a Tesla bank. And so energy storage obviously pervades both the generation, the transmission, and the distribution. I think what's important to note is that though the Tesla-type batteries are certainly getting market intrusion, they're probably not going to be the grid storage technology of the future. Now, cost is a major issue. The grid storage cost really needs to be lower than lithium-ion offers, and you can argue that Tesla batteries are dropping in cost. But where grid storage is today is typically in vanadium redox flow batteries and in high-temperature sodium-sulfur batteries. This just shows the battery development, the battery installment in Tsukuba by NGK. In today's day, people are looking at this material, lithium iron phosphate, and as I said, of course, the Tesla Powerwall for these storage technologies. And one also has to consider that there will be home batteries. These could be sort of at a microgrid. But for these technologies, arguably, the Tesla or even this lithium iron phosphate system is really not necessary. These are non-aqueous type systems where you have an aqueous electrolyte, and if these are put on scale, for example, at a solar energy facility, which is in a hot area, for example, a desert, these batteries have to be air conditioned. They literally cannot function under these hot requirements, under temperature extremes. And they don't function very well at cold temperatures either. So while they provide a stopgap measure, I think to get a lot of technology on the mainstream with respect to storing intermittent solar energy, as I said, they're not really necessarily ideal for the future because of that problem of air conditioning. So in this case, aqueous cells have many advantages. And I'll just tell you about one of them that we've been developing, which is on zinc ion batteries. And, the Volta Peel developed in 1800 was based on a zinc battery. And it's still popular and very important today because zinc has all of these characteristics that I show you here. And in particular, the window that you can establish with zinc metal is actually fairly high due to the overpotential for what we call hydrogen evolution. And so you can use a zinc metal anode instead of complicated carbon composites and things at the negative side, and then you just have to choose or develop a good positive electrode, and that has to be sort of around this voltage simply because above that you start to get oxygen evolution. So you have a good operating window, but one with limitations. But the best advantage is that aqueous systems and zinc are safe and environmentally benign. So in 2016, we developed, using nanotechnology or nanoscience, these nanofibers of a zinc vanadium oxide, and we did this by some special hydrothermal technology. And the point here is that you can see these hair-like structures that are effectively 200 nanometers by 50 nanometers thick, and they're microns and microns long. So they're even thinner in terms of they have a higher aspect ratio even than something like linguine, for example. So the point here is that the thinness of these fibers allows efficient mass transport of the zinc ions through this structure, which would otherwise be limited if we were looking at micron-sized particles. And the proof is always in the pudding, so especially I show here the results of cycling this for 1,000 cycles. We have extremely good capacity, which is effectively flat, and this is real data showing complete, almost 100% Coulombic efficiency with extremely stable response. And this is just a power graph here, which shows the energy versus power. And where you want to be is high energy and high power, and that is what this system provides. So in short, we can achieve 400 watt-hours per liter for the system. Now, lithium ion is typically higher energy density, but we can pack these cells much more easily, and the cost is many orders of magnitude, well, an order of magnitude lower. And we've written a invited review article on this topic in Joule just this last year. And I would say that this field is growing. We've gone from, in the area of zinc-ion batteries, went from 0 citations in 2016 to over 640 per year now in this field. So then I'll just briefly touch on electric vehicles, where big car makers are obviously really putting bets on battery power, partly because electric motors have fewer moving parts, and the electric motors are quite a lot more efficient than your typical internal combustion engine. So it's a 90 versus 25%. And if 16% of our travel could be in electric vehicles, look at the gigatons of CO2 we could save in terms of emissions. This is from CNN. So this is a pretty strong driver for this technology. So we go back to our battery with our positive and our negative electrodes, and we look at an energy. This is a voltage scale of lithium versus a typical positive electrode material. As I said, this is at very high voltage. The problem with these electrolytes, as I mentioned, is that, first of all, their voltage is limited here because they decompose beyond that, but they decompose in a way that produces very resistive layers on the surface of this positive electrode. And this causes fires. Here's an example of a Tesla battery, and I'm just not dismissing Tesla, this just happens to be a Tesla exploding in a parking lot in China, and this is causing serious concerns to car makers who fear that when the market intrusion of electric vehicles really becomes high, the amount of these accidents that are going to occur is really going to diminish the appeal of systems. So increasingly, solid-state electrolytes are becoming the next thing. They have no flammability, so they offer improved safety, and almost the best is that you can pack a solid-state battery much more easily than you can pack the individual cells, for example, in some sort of typical battery pack module. And if you can combine these with metallic lithium as the negative electrode, then you have at least a 70% higher energy density on top of that. And they can be used with next generation sulfur chemistries, and the best thing is that they actually have really good low temperature performance, much better than typical conventional lithium ion cell. So this is just data from Grandview Research, which is considered one of the better market assessment companies. And this is on solid state battery market size. This is valued at US $32 billion in 2019 and expected to grow at a remarkable compound annual growth rate. So they work sort of like a typical liquid cell, except that instead of a liquid electrolyte, there's a solid electrolyte. And this solid electrolyte is mixed with the positive electrode material at one end and maybe the negative electrode material at the other. So instead of having a liquid permeate this porous structure, now we have to have a solid permeate this solid structure. And so that leads to what we call problems of the interface, namely that lithium ions and electrons have to get to this positive electrode material simultaneously. So while the reactivity is not a concern, achieving simultaneous electron and ion transport at these interfaces is a challenge. And this is where we desperately need nanomaterials. And we need solid electrolytes, these yellow things here, with high ionic conductivity that a benchmark is typically about 1 millisiemens per centimeter, which is a metric for conductivity. And we need to control the interfaces. So one of those interfaces is especially the stability of these electrolytes with the active cathode material. and I won't have time to talk about the stability at the other side. So one of the things that we have to do actually is create coatings around the cathode material in order to inhibit that reactivity, and I'll be discussing that briefly. So the first thing my group developed was a conductor with actually not just above 1 millisiemens, but above 10 millisiemens per centimeter conductivity. And this is through chemical design of a new class of materials. And I show you here the conductivity as we tweak the composition, going from very low to above 10 millisiemens per centimeter. And even at minus 78 dry ice temperatures, the conductivity is at 0.1, which is not quite the benchmark, but it's still the highest reported to date. And when we press these pellets, we can get conductivities upwards of about 20 millisiemens per centimeter. So these materials we're using as separators in our cells, so we're using them for this yellow portion that I show here. And then, as I mentioned, there's this reactivity of the electrolyte with the electrode material, and indeed the material I just showed you has that. So one has to, in principle, passivate that surface. And this causes issues for manufacturing. So what you'd really like to do is use these materials for the separator, which is what we're doing, but develop different materials where you can use a naked cathode material without having to put on a coating. And so we've been developing this technology as well. And papers are shown here. We've been working on this with BASF, and we have, I think, 5 patents in this area now. And so the point is that if you use halides as opposed to the so-called sulfide materials, this is a cyclic glutamogram for anyone who's a scientist there, but the point is that we push this potential, this stability potential now into the window where the cathode material is at a commensurate voltage stability with the electrolyte. And so we have coating-free cathodes. We don't need to put any complicated passivating layers on these. And so these are these halide structures. I showed you actually a picture of what they look like here. So these are the cathode active materials, and these little lumpy parts are the cathode, are the electrolyte, which is literally coated and packed onto the cathode active material. So we assemble cells in our lab on a routine basis where we have our cathode composite, which is the electrolyte and the cathode. We have our separator, which is the material I just told you about. We marry this with a negative electrode, either lithium or lithium-indium. And we have, this is probably a record now. This was just published in 2020 of a solid-state battery using a new type of halo spinel, where we're achieving 200 milliamp hours per gram. And this is only over 70 cycles, but this is obviously very recent data. So this is using that other material I told you as a separator and these new coating-free cathode materials as the electrolyte. So with that, I would just like to end off by pointing out that battery nanomaterials and nanotechnology, nanoscale and interface control is really critical for the battery part. That can enable energy storage of renewables, and that actually extends to an integrated energy system, ecosystem, which is mentioned by Dr. Sips, which is, of course, highly important for our future sustainability. So those are, to a large extent, all based on nanotechnology. And with that, I'd like to thank my team, my research team, who did all of the work, the Waterloo Institute for Nanotechnology, and especially BASF in Germany and Canada for funding our work, and CERT in Canada, and we're part of the Joint Center for Energy Storage Research in the USA. Thank you for your attention.
Thank you, Linda, for your terrific talk. So let me take this opportunity to introduce our next speaker. Pieter Telleman is the Business Director of MESA Plus at the University of Twente. We'll be talking about Triple Helix Government Industrial Research Institute. Pieter.
Thank you very much, Shanta. We had a few swaps in talks, so I'm wedged between two electrochemists, but I will talk about activities and innovation at the MESA Plus Institute at the University of Twente in the Netherlands. So good morning, good afternoon, good evening, wherever you are on the planet. For those of you who are not familiar with the University of Twente or the MESA Plus Institute, let me just quickly point out where we're located. We're pretty much on the border with Germany in the eastern part of the Netherlands. And just to give you a feel for the activities that we're doing at the university, this is kind of the overarching themes, I would say, of the university. And the reason that I'm here today is the fact that one of 3 institutes, the MESA Institute, is working on nanotechnology in the widest sense of the word. So there were a lot of activities in different areas, and we're trying very hard to also get these activities rolled out in some commercial fashion. Now, just to give you a bit of an idea, and if you saw the talk by Ronnie van Oever in the previous session, we have quite an established ecosystem in the Netherlands as a whole, and obviously MESA Plus is part of this ecosystem. But we kind of make a drawing, cartoon of the ecosystems that we live in. In the center, you see the MESA Plus Institute together with its clean room. And as we were drawing this up, you can see that it's quite a complex mix of actors, customers, people going through our institute. I will go into the different parts of this cartoon. I just wanted to make sure that you see that we have interactions with a large number of different organizations and different knowledge institutes. Well, to start off with, and this will be familiar to all of you, somewhere in the previous century, it became apparent that knowledge is a good thing to have, but it also translates to capital if you do it the right way. And quickly that translated to valorization or innovation as a major KPI for universities. And as I said, I'm sure that all of you are facing the fact that it's looked upon very positively if you can also translate your know-how to commercial activities. Now, traditionally, universities aren't the most best of doing innovation, so we were known in providing solutions in search of a problem. And on the other hand, if you have companies, they do it the other way around. They start with the problem, customer faced with a problem, customer looking for a particular solution, and they work backwards towards the technology. Combining both in so-called triple helix, I'm sure you're all aware of this nomenclature. So the triple helix entered, combining the strength of university, combining the strength of industry, and having government in there as, I guess, as motor oil to make things work. So the combination of the 3 public-private partnerships, also probably something you're familiar with, PPP, allowed for a model of improving on innovation done at universities. And to make that possible, also at the University of Twente, we have started working together with different partners in the region. You see them at the bottom of the screen in a collaborative effort called Novel T, where we as a university can find the people that have know-how of IP, of seed funding, how to proceed, contacting companies or other organizations that you need to successfully commercialize know-how. And if we look back over the lifetime of the University of Twente, which is not that long, it was established in 1965. There is about 1,000 startups and scale-ups located around the university. I guess 2 of the more familiar are Booking.com, which you'll find here, and Thuisbedorf.nl, which I guess is better known in the Anglo-Saxon world as Just Eat, a company which is now expanding to virtually all continents. So quite a few large companies as well. And in fact, every second year in the Netherlands, universities are analyzed to see which one is best at commercializing, valorizing its research results. And for the first time in a row, the University of Twente has been named the most entrepreneurial university of the Netherlands, which is indicated here with these three guys. So that's University of Twente as a whole. When it comes to innovation at the MESA Institute, so regarding nanotechnology, We just celebrated the 30-year anniversary of MESA and the 20-year anniversary of the MESA Plus. We have about 50 startup companies specifically working on various aspects and applications of nanotechnology and microtechnology. So also there you'll see that working the triple helix together with industry, together with government, this worked very nicely. However, I just want to draw your attention to the fact that as Triple Helix have been working the last decades on making sure that know-how translates to the society in some manner, we're now seeing some pushback. And here's an example from the Netherlands from very recently, a couple of months ago, that there is a pushback on the rollout of the 5G network in the Netherlands because it has been associated with a variety of negative effects like cancer, even COVID-19 was thrown into the mix. So somehow we seem to be losing society when it comes to rolling out technology in our society. I guess in case of this particular example with 5G, you could just talk about a few crazies, but we also see now, and this is also very relevant, I guess, considering the fact that if things go right, we'll be having a vaccine to COVID-19. We also there see a considerable pushback from society to new technology. And you can see it in the right-hand corner. It's about 30 to 50% of society turns down or is skeptical of the vaccine safety. So this is a considerable problem, I guess, which has been developing over the last decades, which we also need to address as a university. And this is where you see that we're moving from a triple helix to a so-called quadruple helix. It was already mentioned in a previous talk as well, where the citizens are thrown into the mix. So they have to be informed, they have to be involved, they have to know what's going on. It requires transparency of the university to make sure that you win their trust when it comes to rolling out new technologies as well. So, and that's not just true for society as a whole. Even more recently, the quintuple helix was launched, throwing into the mix the environment, sustainability. As you all know, in the last year, we've seen quite a lot of rise up of youth with regards to the environment, taking environment seriously. So also beyond the triple helix, we're seeing the quadruple helix with including society as a whole, and now the quintuple helix, making sure that also activities are sustainable in the future. So at the University of Twente, we're trying to do our thing in making sure that we also address the quadruple and quintuple part of things. And I would like to just give two examples. We started a science cafe where people are invited, so society as a whole, as citizens are invited and listen to talks from people from the university about various topics going on at the university. So here are two examples. One is the impact of social media, and the other is the Internet of Things. So just two examples from that particular science cafe. And the one I'd like to show you here is the university tent, which is a tent of the University of Twente at one of the festivals in the Netherlands. And the reason that I like to show this particular one is because it allows me to show two comprising pictures of my next colleagues, scientific directors of the MESA Institute, which is Guus Reinders, who will speak later today, and also Albert van den Berg, who's listening in, and he will also give a presentation a little later today. So again, this is a way to bring science to the people and kind of break down that that threshold, which apparently is present in this pushback from society in particular topics regarding science. Now, it's not the only pushback. I guess at least we are confronted with the fact that in increasingly scientific project proposals require this PPP approach, which also involves significant co-funding from the private corporations included in those collaborations, making it more difficult in practice to start working on projects which are purely curiosity-driven or which are basic research. So we are seeing this in the Netherlands, that it's getting more difficult to have curiosity-driven research going on, and we see a shift towards this private company involvement, so the triple helix. So I guess also there, as a science, people in science, we need to push back and make sure that also the case for curiosity is curiosity-driven science still is made. Now, regardless, we've seen the triple helix, we see quadruple helix, the quintuple helix, and now even people talk about n-tuple helix. So ever more different factors are thrown into the mix. I guess what needs to be done is we need a transparent university more now than ever. I've shown you two examples of pushback from society to developments in science and in technology, and we need to avoid that. I guess with nanotechnology, we are addressing so many different issues in society, problems in society, and if we want to make sure that when we have solutions for these, that they're also accepted by the customer out there in society. So transparency is key. And that was my last slide, Shashantak.
Okay, thank you so much, Pieter. Let me take this opportunity to introduce the last speaker in this session 3 before we have a morning break here in Waterloo. It is my distinct pleasure to invite Dr. Professor David Sinton. He's a professor in the Department of Mechanical and Industrial Engineering at the University of Toronto. David, please.
Great, thank you so much, Ashanta, and thanks for the invitation. All nice to see you. One of the great things about our digital environment is we can be teaching class 1 hour and then in Toronto and giving a lecture or a talk in Waterloo the next. The problem with that is that we actually try to do that, right? So, anyway. Okay, great. So happy to be here, and you can see this screen okay, I hope. So I'm going to talk on electrocatalytic systems for CO2 conversion to products. This is a topic we're passionate about, and it's an example of scaling, really. We nanoscale science and microscale transport, nanocatalysts are essential for this work, but also essential is making this stuff big, right? Like all challenges in the energy system, they're fundamentally very large scale. So that gives, I think, all researchers in this area pause. It gives me pause for sure, because I'm really a small scale transport person. I'm a mechanical engineer, and that's really where I've got my training, and that's where I have expertise. So small scale expertise, very cognizant and very insecure in a sense, because the challenge is huge. So let's think about the scales of global energy for a slide or two. So this is the global energy mix. This is the best data we have from the Statistical Review of World Energy. This is what we used last year as a globe, all in. I apologize that one little guy at the top slipped over, but that's solar at 1%. Doesn't seem like much, but by the way, that's a huge rate of change increase there is absolutely incredible. And the scale of the energy system is so large that getting on the board here is not easy. Nonetheless, the rest of this, it doesn't change too much. I teach a course in in mechanical engineering, and it's about current energy infrastructure. And the idea was that every year I'd update this chart, and I update it, but I don't really need to, right? Because it doesn't change much. The energy system is very large, very difficult to change. It needs to change. It's just slow. Why does it need to change? Because, of course, CO2 impacts, right? So the current mix, we're about 85% fossil fuels. That's what supports your way of life. That's what supports mine. And the challenge with that is the many billions of tons of CO2 that we produce. And then again, maybe it's my insecurities as a small-scale transport person, but I think about the size of 1 ton of CO2 even, right? So this is 33 billion. Even 1 ton of CO2, it's a big thing. There's some neat demonstrations around the world that show you how large your 1 ton of CO2 is. Maybe the best thing I've done in 2019 and 2020 is not fly so much, so I've avoided some of my tons. My lifestyle is not elaborate. It's very typical for an academic. I'm something like 20 tons a year, typically. Many people in the audience will be roughly similar. So that's the CO2, or that's the overall picture. So where's this energy used? This comes from this is a really nice chart from Lawrence Livermore, a famous chart, and there's a lot in here. It shows you natural gas goes into a bunch of different sources. It's really embedded into almost every major sector. Coal just goes to electricity production only. It used to do different things, but now it's just electricity production. And then oil. Oil used to spread across this chart too. When I was younger, right, oil did a lot more residential heating, did a lot more commercial stuff. It's been beaten into just industry and transport. Why? Because these are essential. These are areas that it's hard to get it out of. It's hard to take where it has the value of petroleum is in the energy density for the most part. So that's why it's sticky in transportation, but we're all hopeful that electrification is coming on board faster and faster, and it can finally be removed from the transportation. That will take time. Where's the CO2 used? So there's a few major sources of CO2. I'm a San Pellegrino guy. Perrier is okay too, but I'm really a San Pellegrino person. I guess when I was a kid, I was probably a Pepsi person, or was a Coke person. Now I'm a little bit healthier. So that's up here, right? That's beverage carbonation. So that's a fairly major use of CO2, right? The current food industry uses a bunch. There's a few other sources. But what's this big blue? Does anyone know what this big blue section is in terms of uses for CO2 globally? Stressing you guys out. I'm not sure I can even see the chat. That big blue block is oil and gas. So it's currently used for enhanced oil recovery. Quiz question number 2. Maybe you can tell I just came from a lecture. Where's the biggest CO2 project in the world? The absolute biggest CO2 project in the world. Think of nations that are leading the charge on using CO2 in industry. Yeah, it's Canada, right? And don't be sad because no other Canadians know that either, or about 5 of us do, I think. But Canada has the largest CO2 project in the world. It's the Weyburn and Midale fields. They inject this stuff underground. It goes into these oil formations, and some of the CO2 is stored, some of it is freed, some of the oil sticks around, some of it is freed. It's this complex combination of environmental and economic benefit, and it works for some types of oil reserves, and this is an example. Interesting technology, and important, ultimately, but sometimes we think maybe it doesn't have any fans. Environmentalists see it as kind of a mixed benefit, right? You're ultimately producing oil, but you are storing CO2 at a scale that nobody else does anywhere. That's good, I guess, kind of mixed good. And then the oil guys, they say, yeah, this is kind of good, right? But it's too expensive. The CO2 costs too much. So anyway, this technology makes nobody happy, but in some fields and for some environmental benefit, it is useful. Okay, so this is our early work. We really started here thinking about, well, we're small-scale fluids people. Can we apply what we do to high pressure, high temperature conditions that are relevant for CO2 operations? And this is really CO2 utilization. We just answered the question, where's CO2 used worldwide? This is where it's used worldwide. and can we help that process? And we developed a bunch of stuff. I'm not going to go in detail today. This was a chip that helped us see, fluid properties. It's fluid measurement, plastic mechanical engineering kind of stuff. What's the phase of this mixture, this industrially relevant CO2 or oil CO2 mixture at a particular temperature and pressure? So it did a good job of that. And then the top one is just a nice plot that's actually a real, not a computational plot, but actually a visualization of fluid in a porous media. That was a nanoscale porous media, and that helped us understand how fluid's moving in those formations. So this work has been translated. There's a company, Interface Fluidics, and they're in Calgary and in Edmonton, labs in Edmonton at NINT, the National Institute for Nanotechnology. They've been a great landlord for us and great facility. And then our business offices are in Calgary, and this is getting some traction. So we sell to the biggest companies. I was going to say biggest energy companies, but some of those are the biggest companies worldwide, period. And the ones above the line are energy companies, and the ones below the line are chemical companies. Chemical companies want to use our systems to test how their chemical does in a particular situation, or a solvent, or nanoparticles, or whatever. And then the oil companies want to know how well it could work, and they also want to know, how much reduction can we have in costs? How much the chemical supplier says we need so the X concentration of this chemical. Can we get away with half of that? Can we have some savings? And those savings, by the way, are large when you think about the volumes of chemicals that these huge organizations use. So there's real savings. It's an efficiency play, but there's savings there, both environmental and cost savings. So that's going okay. And it's been the Creative Destruction Lab was an important incubator for us, and then we moved to Techstars Energy, Oslo, Norway for 4 months, and then launched this thing. So if we move to looking forward, which is what my lab is doing now, right? So the company is launched, they're doing their thing. If we think about transitioning from current energy sources, we talked about those, our current energy mix, to a future energy mix. And thinking about not just using CO2 where we've used it to date, but actually converting it. So that's the forward-looking challenge that my lab has been working on over the past few years. And the first question you have to ask when you think you're going to convert CO2 and you want to convert CO2 is into what, right? What should you make? And really, to me, the answer is pretty clear. You can make all sorts of things, right? And you can make it. And there's lots of neat technologies, and I don't want to cast aspersions, right? If you've got a cool company coming out of a university that's making, glasses frames, right, out of CO2, that's cool, right? You should do it. I'll probably buy some of those frames. Maybe it has a little CO2 on the side or something. That's awesome. But what? How many tons of glasses did you buy last year? Well, not much, right? Maybe zero, maybe 0.00001 tons. How many tons of CO2 did you produce last year? We talked about probably 20 tons, 10 tons, something like that. So you need, when you're thinking about what we should make with CO2, you just have to ask yourself where it came from. Like, how much did you produce? So you have to make something that you used tons of last year. Does that make sense? You, me, everybody. And there's not too many of those things. We didn't buy tons of much, right? We bought tons of fuels, but tons of water. It's pretty hard to make water from CO2. But really, what did we bought tons of fuel. And you may be thinking, I don't remember a huge barrel of oil being, shipped by Amazon to my condo. Nope, it didn't, right? But the energy system working in behind you, supporting your lifestyle and your transport and your flight to Florida, did buy those barrels. You did buy those barrels. You did buy that natural gas. And it's those fuels and feedstocks that have supported your lifestyle last year that produced the CO2. That's the stuff you have to make, right? If you want to have a practical CO2 solution. You can make money making glasses out of CO2, and you should probably do it, and it's a good idea. But it's not a climate solution, right? Climate solutions are the things we use tons of. All right. This paper in 2018, I think, gives us a really clear picture of what we with current energy system and what we need to do. So we've got lots of CO2 available. That's not going to change. We hope it trims down, but it won't happen quick. Low-cost renewable electrons. This is a big one, and I know this topic has come up in this conference already, as it should, right? This is amazing drop. This is a log scale in cost of renewable electrons. So that's totally different than my undergraduate education, right? Which was electrons are at the top of the heap. You burn chemical energy to get the electrons. That's the deal. That made sense for a century or two, but this is changing the game. So there's now renewable electrons available, and increasingly so. But there's long-term demand for hydrocarbons, fuels, chemicals, feedstocks, plastics, all of it. So can we take this CO2 and low-cost renewable electrons and make these things? Again, would have been crazy 10 years ago. Getting less crazy with cheap renewable electrons. So the approach is, it looks familiar to folks at Waterloo and elsewhere. This is an electrolyzer, right? So this is just an electrolyzer that takes in CO2, water, and produces stuff, so it reduces the CO2. A quick tour of our early work here. We started small. We started on the nanocatalyst side. This work is in partnership with Ted Sargent's group, and they led this paper. And this is really our first big group on these nano-structured needles, and they're cool, and they've got some cool physics, and they had some cool results for CO2 to CO. Where we've invested more, we being my group, is looking at maybe the scaling systems around these things, right? So electrodes was our next big step, and trying to design electrodes so you get all the things you need. Those good mechanical engineering, chemical engineering bits, right? The transport of reactants, the transport of products away, transport of electrons, all of those things to the catalyst surface. I should highlight a couple honorary Canadians here. Din is at Queen's now, and Tom Berdini is at Technical University of Delft. So Netherlands connection there now. And now we've really moved towards macro-scale systems. So thinking about beyond the electrode, we've got nanoscale catalysts, microscale electrodes, bigger systems, and I'm going to show a few slides from our biggest systems we've got. And here we're making ethylene and ethanol mostly. Made some propanol. We can make CO, make formate, a few others, but really I've focused on ethylene and ethanol, C2 products that have a big, major global market. Great, so we really divide our work into three areas. I try to think of the cell as at the center. That's where the technology is, but we need to look upstream of that and downstream of that. So I'm just going to walk you through a couple examples here in each step. So one example in the input side. What we want on the input side, think of it like a business. You want to take as input the cheapest possible stuff, right? If you need something really expensive as input and you're making something that's a commodity, you're in trouble. So cheap CO2 is low purity CO2, right? And ultimately probably even got some nasties in it. Let's start with the low purity aspect. Oxygen. Most streams, industrial streams of CO2 have oxygen in them. Typical levels are on the order of, like half the CO2, kind of one molecule of oxygen for every 2 CO2 molecules. So that's a lot, right? And the issue is that oxygen is reduced readily. So it can really divert and distract from CO2 reduction. So that's a challenge. So our vision here was if we could make a step towards flue gas reaction directly, taking that super cheap input. So here's CO2 and O2, and this stream are 15 to 4. And you can see here when we add that O2, and you can see in the far, hopefully you can see my little mouse here. If we've got 50% stream of O2, we can react it decently when we pressurize the cell. That's not impossible. But we add that O2 and our Faraday efficiency just drops to 0 because O2 just takes over, right? Oxygen reduction. So the solution was to protect the catalyst, right? To protect the catalyst in a way that was somehow switchable. Is there a way to invite CO2 to come in and react and push away the oxygen? And the answer is, the best tool we could do to find that was in the mechanical and chemical engineering toolbook, playbook, was to look at the difference in CO2 and oxygen solubility and had a hydrophilic layer next to the copper that can still allow CO2 but greatly discourages oxygen. So that result, we were able to get really decent ferritic efficiencies back and decent current densities back, actually competitive with the best systems that don't even have oxygen in them. So we were able to totally ameliorate that issue. Conscious of time here, I want to show you just one example in the cell, and then I'll skip a couple slides and I'll highlight some work on the X prize scaling. So this is can we make the cell more efficient, right? You got to take electrical energy input. Yes, it's getting cheaper, but it's not free. So this was a case where we were able to choose 70% energy efficiency. So 70% of our electrical energy input went into chemical energy upgrade from CO2 to CO. And this was just mechanical engineering again. Reduce your electrical, I guess. Reduce your distances, reduce your conduction paths, right? And just eliminate resistances, and with that we were able to get to some industrial relevant current at really good efficiencies for an energy conversion system. So that was a win. This work I'm going to skip over, but it's not fair because Adnan is on the left-hand side here, is an absolutely wonderful grad student who is a U of T from the University of Waterloo grad, comes from the Shanglo's group, and is outstanding. And what he brought to our group and our collaboration was just fuel cell excellence, good ionomer engineering that really enabled us to get CO2 better transport of CO2 to the catalyst surface, and increase basically the size of that reacted cell. Last step, I just want to touch on the output side. We're competing in the Carbon X Prize, and this is, some of you know, heard of X Prizes in the past. These are big, hairy competitions, and they're neat in the sense that they just give a big goal and they don't give a damn how you get there. So in this case, it's convert CO2, make it into something useful, and do it efficiently. And they don't care what you make or how you make it. So our group is in the finals. This is the University of Toronto Carbon X Prize team, otherwise known as CERT. Christine's my postdoc. She leads the group, and this building is out in Calgary. When we made it to the final X Prize round, they said, "Great, here's your gravel lot. Good luck." So we built this building here, and inside it houses this plant where all the exciting technology happens. So these are power supplies underneath. These are cells. And to give you a sense of scale, most academic cells in this realm operate on 1 centimeter squared, some 5, sometimes 10. When we run a bigger one, sometimes we like to run 50, and we make a case in the paper that this is sort of showing scaling, right? This is 40,000. When this thing is running full out, there's 40,000 centimeters squared. It is the largest CO2 to ethylene conversion system in the world. Here's a quick walk around tour. There's a little control system here, and you can see these power supplies. It's really just a big mashup of chemical engineering, electrical engineering, and mechanical engineering, transport, big electrolyte tanks of CO2, et cetera, et cetera. Separation columns on the output. Great. So we're down on time, so I'm just going to jump to the conclusion here. Energy and environment are, to me, the fluids challenge, and one that is worthy of great attention. All solutions must scale ultimately to the gigaton level, right? So that gives us it guides us a bit, right? We don't have to worry about whether we should make sunglasses or not. We know the answer. We need to make fuels and feedstocks that we use at the tons per year level. And then CO2 conversion, that I think there's a hope for this technology that we can take CO2 and convert it efficiently into products, and gave an update on to where we're at in that process. Thanks to my team here on the right, funding agencies, of course, and the work, especially on the catalyst excellence side, which would not be possible without great collaborators in Ted Sargent's group. And thank you for your attention.